Okay, coming to the end of week 4, and today we are going to do the chain rule. So, as you've been noticing, we've been just learning lots of rules. So this chapter 3 of the text is kind of a little bit technical, where we're just learning all the different ways to differentiate functions. So remember what we're doing. We're learning how to differentiate the little parts. So we know how to differentiate powers, we know how to differentiate exponentials, and we're also learning how to differentiate when we combine things. So we know about when we add functions, we add the derivatives. Okay, so today we're going to do something called the chain rule. And this is a case where you multiply derivatives. But it's not the derivative of the multiplication of functions. We'll do that next week. We already know how to multiply derivatives. It's a pretty straightforward scenario. So let's say we run a bookshop. We sell 10 books per hour, and we make $5 per book. What's the rate at which we're making money? If we're selling 10 books an hour and we're making $5 per book, how many dollars per hour are we making?
Making $50 an hour.
Exactly. And how did you get to that?
Multiply the number of books by the cost or the price per book.
Right, because if we write it like this, 10 books per hour, $5 per book, it sort of becomes transparent, right? Because the books disappear and we're left with $50 per hour. Okay, so we didn't really need any great math to do that. That's just sort of understanding units, really, enabled us to do it. Okay, so now I'm going to go with something really simple with something really complicated in one step, but it's exactly the same thing. Okay, so let's say instead of selling 5 books per hour, let's say we, what was my example? Let's say we sell T-squared books per hour. All right, where T measures hours, and we make x e to the x. Let's make it dollars per book. Where x is the number of books. Now, this is really silly. We can do exactly the same thing, right? We're just going to multiply them together. This is a rate, this is a rate, and so we get, what do we get? We get e to the x dollars per book times t squared books per hour. And exactly the same thing happens. We're going to end up with e to the x times t squared dollars per hour. Even though that looks just so bizarre, that must be the case, right? Because the units match up. There's one little thing that's wrong with this. What's wrong with this expression, which is not how we like our expressions to be? We've got x and t in there, right? Because usually when we have functions, we like to have just one input. So, but we can see here actually, t squared books per hour, x equals t squared. So x equals t. Still looks strange, but it's true. Okay, we've done it. And that's kind of like the only hard bit that we did, right? Was turning that x into a t squared. Okay, now, what have we done here? We have multiplied rates together, and we could do this because what happens? What's the process? Okay, so time is our input, right? Hours. What happens? Hours gets turned into books by this. Books gets turned into dollars by this. This is the chain of the chain rule. So whenever you have a chain and you have a rate here and a rate here, so this is rate 1, this is rate 2. So rate 1 is the, is the rate that this is going. Rate 2 is the rate that this is going. This rate is rate 1 times rate 2. Okay, so that's the backdrop. Let's do things in terms of derivatives. Okay, so here you notice we did a dollars per book, books per hour. We've got dollars per hour. Let's get rid of this expression. Let's say we have, let's call these, let's say, what was it? This was a t, this is an x, and let's call this y variables. Okay, the rate at which we get money per hour is dy dt. That's just the rate of change. What am I saying? It's equal to this rate times this rate. Well, what is this rate? This rate here is the rate at which you do books per hour. That's dx dt. And then we've got the rate which turn books into money. That's dy dx. And that's the chain rule. Okay. So hopefully you look at it and you see it makes sense, because it looks like the dx's cancel out, right? Because how are we figuring out these derivatives, right? We're doing a little rise over run, a little rise over run, but here the rise is equal to the run here, so they cancel out. And so we get this rise over run, and that's the derivative. Okay, so that's it in the Leibniz notation. What is it in the, this notation. Okay, so here we've got, or let's call it y prime. Let's not introduce too many new letters. So this is derivative with respect to y. This is x prime of t. This is the dx dt. And this is y prime of x. Just doing the same thing. We've got the same problem as before. Here we've got two different variables. We've got a t and an x. But it's okay because x is some function of t. So we can write this as x of t. Looks like I'm just doing magic spells, right? But let's, another way of writing that would be to say that f, so let's completely new example, f of g of x, what is the derivative of that? Does anyone remember what they call this kind of thing where we put one function inside of another? Nesting. It's nesting, but it's like a musical term. Composition. We compose, so you've probably heard that. That is equal to f prime of g of x times g prime of x. So instead of this, I think this is more useful. So these are the two ways that you can think of the chain rule. And this is a thing that always confuses people. Why is that g of x there? And the reason is you have our chain. We go x, we go to g of x, and we go to f of g of x. This is this rate of change here. G prime of x. It's how the rate at which x gets turned into g of x. This is this rate of change here. And the reason why we have to have g of x in here is because that's where we are in the chain. Okay. So now that I've nicely confused you, but we do some examples and that will unconfuse you. Okay, so let's write this down. Let me try and be organized. So on the so the people at home can follow this. I'm going to put the chain rule here. Chain rule is dy dt equals dx dt times dy dx, or f of g of x equals f prime of g of x. Okay, let's do some examples. So I think the chain rule is the most important of all the derivative rules. That's me. So let's write down something that we would find very hard to differentiate before today. So let's have a look at e to the x plus x to the 7th power. Okay, so this is a function that, wow, it's just so complicated. How are we going to differentiate it? Well, the way we differentiate it is we think of it as a chain, right? So how would you do this in your calculator? First, you'd figure out this. then you would raise it to the 7th power. So we take our x, we would take it to e to the x plus x, and then we would take it, so let's call that u, just as an intermediate step. And then we take this to u to the 7th. So what I've done is I've broken it up into tasty little morsels of the function, right? Because this bit and this bit are things that we know how to take the derivative of, even though we didn't know how to take the derivative of the whole thing. And since it's a chain, we just multiply those derivatives together. So what's the derivative of e to the x plus x? What's the derivative of e to the x? E to the x. Just e to the x. What's the derivative of x? Yep, just 1. Okay, that's that rate of change. We multiply it by this rate of change. What's the derivative of u to the 7th? Just the power rule.
Is it 7 to the 6?
7u to the 6. Exactly right. Okay. Still got our problem. We've got u in here, which is something we just made up. So we've got to get rid of it. But that's okay because we know what u is. So that's equal to 7 e to the x plus x to the 6. Just writing this again. And just multiply that by that. E to the x equals. And that's derivative, believe it or not. I always find these kind of neat. Because that's a really nice thing about these derivative rules. You come in, you've got a function, oh, how do I differentiate this? And then you just break it up into its simple parts, use the relevant rule, and then you know how to, as long as you know how to differentiate the relevant parts, you can smoosh it all together and get the big derivative. Let's do it.
So on the chain, you made the first part x. Is that always just going to be a variable? The first one.
It's whatever the variable is in the problem.
Okay.
And typically, I always use u for the intermediate step because we hardly ever use u for anything else. So it's just something which is, you know, just what I do. Okay. Has everyone got this? Okay, let's put some functions together in another different way. Let's see if I can do fit 2 on the board. E to the x squared plus x. And ln of x squared plus x. Okay, again, they're complicated looking functions, but again, we can break them up into easier pieces. Okay, again, both chains start with an x.
Are these 2 separate examples?
These are 2 different examples.
Okay.
I thought you were wanting us to combine them.
No, I was just trying to do it. Okay, so let's come up with a chain here. So what do we do first with the x in this problem here?
Just make it x squared plus x.
X squared plus x. I'm going to call that u again. And then what's the second thing we do? E to the u. A nice chain, right? Complicated, simple, simple. That's what our chain has to be. Let's do this chain. what would we do here? X squared plus x. Again, I'll call it u, but this time it goes to ln of u. Okay, so doing the chain rule is kind of like you just have to look at the function and you have to it's like parsing it. It's like something you would do in English with grammar or something. You have to break it up into its constituent pieces. But once you've done that, then you can take the derivative. What's the derivative of x squared plus x? 2x plus 1. The derivative of e to the u? E to the u. We don't want the u because that's just something, it's just something we just use just for the thing. So 2x plus 1 times e to the x squared plus x. And we're done. Okay. Let's do this one. Derivative of x squared plus x. 2x plus 1. Derivative of ln of u. 1 over u. Got to do the same thing. Change u back to x squared plus x. We're done. Okay, so
I have a quick question.
yep.
So I understand like how we did everything, but how did you know like how to set the chain up?
That's right. You got to look at the function and you kind of do it in the order in which you would calculate it. So here we've got x. What's the first thing we do? Is we make the exponent. So that's why I do x squared plus x. Okay. So what's an example? Let's do an example of something which is say we have ln of x squared and ln of x squared like that. Okay, so both of these use the square function and the ln function. Okay, so the difference is in which order you use them. So in this one, which one do you do first?
The x squared.
You do the x squared first. In this one here, which would you do first? You do the ln x, right? So here the chain is x goes to x squared, let that be u, and that goes to ln of u. This one, the chain is x goes to ln of x, we'll call that u, and then that goes to u squared. Okay, now we take derivatives. Derivative of x squared is 2x. Derivative of ln of u, 1 over u. So that equals 2x over x squared equals 2 over x. Because of course ln of x squared by the log laws equals 2 ln of x. So we could have saved ourselves some trouble if we'd seen that, but that's beside the point. This one here, derivative of ln of x is 1 over x. Derivative of u squared, 2u. So u is ln of x, so it would be 2 ln of x divided by x. They're different, which is good because they're different functions, right? It all depended upon which order we did the chain. So that's the main thing you got to worry about. You got to look at it, you got to figure out which comes first and do that first. But you'll notice that after you do a lot of these problems, the same chains come up all the time. So for example, you might get, I'm going to try and do 3 this time. 1, 2, 3. So you might get a chain which is a power, something power. So it is something, let's call that something z to the n. So z could be anything. It could be a polynomial, it could be an exponential, it could be a log. Right? The derivative of this, so the chain is going to be x going to z to the n. No matter what z is. Okay? And so the derivative then is going to be dz dx times n z n to the minus 1. Right? So for example, if z equals, give me an example of the z.
22.
No, a function.
Natural log of 22.
That's not a function, that's a number. It's got to have an x in it.
Times x.
Oh, that's so boring. Someone give me something more interesting. Because it's just a number, ln of 22 is just a number. So an example could be, x cubed plus 17x plus 1 to the 22. Okay? So by this, it's going to be the derivative of this, which is 3x squared plus 17 times, by the power rule, it's going to be 22 times z to the 21. And we just plug in what z is. So a lot of them are going to look like the same. Or it could look like e to the z. And then our chain would be x goes to z, goes to e to the z. And so then our derivative would be dz dx times e to the z, right? Because the derivative of e to the z is e to the z. So again, if z equals x cubed plus 17x plus 1, again, it'd be 3x squared plus 17 times e to the z. And we plug in what we had for z there. Or it could be ln of z. And again, our chain would be x goes to z goes to ln of z. And again, our derivative would be dz dx for the first step, but now it's going to be 1 over z. So in this case here, it would be 3x squared plus 17 divided by z. So after a while, so it looks kind of confusing, but after a while, it just becomes real rote. You just see that there's so many things the chain can be. Could be powers, could be exponentials, could be logs. Later on, as we can see, it could be trig. There's not much else going on. Okay, so let me give you another example of these. What about 3x squared plus 1 to the 6th? Okay. Again, it's x going to 3x squared plus 1. We'll let that be z, and that goes to z to the 6th. It could be z or it could be u, whatever you use. It's kind of like a dummy variable. Okay, the derivative of 3x squared plus 1 is 6x, right? And then the derivative of z to the 6th is 6z to the 5th, which is going to be 36 times x times 3x squared plus 1 to the 5th. Or we could have e to the minus x squared. So x goes to minus x squared. We'll let that be our z, goes to e to the z. Derivative of minus x squared, minus 2x. Derivative of e to the z, e to the z. And we plug in what z is again, get minus 2x e to the minus x squared. What about ln of x squared plus 1? Okay, x goes to x squared plus 1. We'll let that be our z, goes to ln of z. Derivative of x squared plus 1? 2x. Derivative of ln of z? 1 over z. We get 2x over x squared plus 1. We turn it into a little factory, right? You have one person just doing the chains, another person differentiating the bits of the chain, the other person multiplying together, and another person simplifying.
We don't have a test.
No, I'm just talking about in theory. Okay, you kind of comfortable with this? Okay. So chains, how long can a chain be? It can be as long as you like, right? So typically most of your chains are just going to be 2 links, but it's easy to come up with 3 links. We could have some kind of function like the 5 ln t plus 3 to the 6 plus t. Looks kind of complicated, but we have t. First thing it goes to what's inside. Oh, hang on, this is just one chain, isn't it? No, that's not a good example. Let's not worry about it. No, we should do one more example. square root 1 plus 5e to the 2t. I'm using t as a variable. It doesn't really matter what the label. Okay. Elijah in the back there. Hi. Nice to see you back. What's the first link in the chain then? What would you send t to? So what gets done first with the t? Yeah. 5e to the 2t is good. We might as well throw the 1 in there because the 1 is easy to deal with. Okay. Let's call that, what do you want to call it? U or Z or B or what? What's a good letter for you? U, okay. And then what do we do with the U? Square root it. Okay, that's a nice looking chain. So, who wants to go next? Matt, what do you think? So what's the derivative of this? Okay, so it's a constant multiple, so that stays. What's the derivative of e to the 2t?
Just e to the 2t.
It's e to the 2t times 2. Right, because remember, e to the kt is ke to the kt. And what's the derivative of u to the 1/2?
The same thing if you.
So down comes the power. So what do we write? So what's the power?
1 over 2.
1 over 2. We subtract 1 from the power, what does that give us?
Negative 1/2.
Negative 1/2. Excellent. And then we just multiply these two things together. Okay, the 2's cancel. And we get 5e to the 2t over square root of u. But we know what u is, right? Okay, so one of the things you have to practice is just following the rules. You know? I know you're all good kids, you all follow the rules, but I'm talking about the differentiation rules. So, you know, when down comes the power, subtract 1, you know, it's kind of just mechanical, you know, you're just turning a crank and out comes the answer. And so, using that, as long as you just follow the rules, you can get quite complicated looking things and you can take the derivative of this. Actually, this is actually an example of a longer chain because what we could have done is this way. It's the same answer. So I could have gone from t to 2t. Okay, I let that be u, and then I take that to 1 plus 5e to the u. So because, you know, Matt, you were having a little brain thing, you know, gears were grinding about how to do that. Well, If you break it up even finer, it becomes easier. And we can call that v. And then we can go take that to the 1/2. Right, and then the derivatives are 2, 5 e to the u, and 1/2 v to the minus 1/2. And we would have gotten the same answer. It might have been easier to do. So don't be, just because the chain is longer doesn't mean it's going to be more complicated, because quite often if the chain is longer, that means the parts are simpler. So each part might be simpler to do. I don't want to do. Oh, I do. Okay, sorry. Oh, I know what I wanted to do. Oh, one thing. One thing you might have noticed is let's say we have ln of f of x. Okay, so if we do the chain for this, we get x going to f of x, let that be u, going to ln of u. And so the derivative of f of x is f prime of x. And the derivative of ln of u is 1 over u. And u is f of x. So the derivative of ln of f of x is always f prime of x. So do you remember what we called this?
Isn't that the relative rate of change?
It's the relative rate of change. Yep. So that's another way to think about the relative rate of change. It's the derivative of ln of the function. And that can sometimes be useful. So, for example, we could have one of these allometric problems where we say that the surface area, if we let S be the surface area of a mammal, and M be the mass of the animal, and let's say we have a formula like Sm equals 1095 times m to the 2/3. Okay, so this is just some formula that relates how big an animal is to its surface area. And it's like a 2/3 ratio, and that makes sense, right? Because mass is a 3-dimensional thing, and surface area is a 2-dimensional thing. So to convert a 3-dimensional thing to a 2-dimensional thing, we raise it to the 2/3. So what's the relative rate of change for a 70 kilogram human? Okay, so i.e., if you're a person who weighs 70 kilogram, how much does your surface area go up as your weight increases as a relative change? Okay, well, we could do, to figure out the relative rate of change, we could do f prime on f. And that would be, we'd have to take the derivative of this and then divide it by this. But another way we could have done it is by looking at ln of this. And can anyone see why taking ln would be interesting? It make life easier for us? Because what does taking logs do? Logs convert exponentials to what? It converts products to sums. What does logs do to exponents? Does anyone remember the log laws? Yeah, it brings them down. Okay, so this is a much easier thing to take a derivative of. So this formula is simpler than this formula. Okay, because its derivative is going to be then just 2 on 3m. And so for a 70 kilogram person, it's 2 divided by 210, which is about around like 1 over 100. So that's telling you that if your weight goes up by a kilogram, your surface area goes up by 1%. We all know where that surface area comes from. Okay, so that's the chain rule. I always think it's the most important one, and I think you've got a good sense of it because all of a sudden we can just differentiate really complicated things. Anyway, I'm giving you homework. The best thing to do is just do some examples, and we'll go from there. See you, Joe and Phoebe. No.